desk there at the reception for the party that Deirdre is hosting on Wednesday night at her place. It's maybe a 20-minute walk away or something from here. Anyway, she would like people to sign up if they intend to come, so she has some idea how many people there will be. Sorry? The sign-up sheet is on the reception table just at the front. Just to, you just write your name with a pen. Okay, our first talk today is Omar León Sánchez from the University of Manchester, and he will speak on differential automorphisms and positive characteristics.
Okay, thanks for him. And thank you everyone for showing up at this early time. So I should write the title somewhere. It's about differential automorphisms in implicit characteristic. Well, first I want to thank the organizers, Rahim, Adele, is there, and Jason, for the invitation. It's very nice to be back at Fields. Second, this is joint work with Kai Ino. Okay. And I chose the topic kind of because I saw the title of the workshop and I saw dynamics and then model theory, and I thought, okay, maybe it would be a good topic to say a few words of what happens when you have an automorphism, and that automorphism interacts with some structure. In this case, the structure is differential fields, and say a little bit about that. Okay, so I hope that what I'm about to say, everyone gets a little bit out of it. Okay, right. So what is the kind of motivation? Okay, I could motivate it first from the sort of model theory side, but I'm not doing that. I'm going to try to keep it kind of algebraic, and then at the end I will say a few things about the model theory content of this, but I'll try to keep it algebraic. Okay, so what do I want to talk about? I want to talk about finding solutions, so motivation. Finding solutions to differential / difference equations. Okay, what do I mean by that? What do you mean by finding these solutions? Okay, so first of all, I'm going to fix field K, and on that field K, I'm going to assume that I have two sort of operators. One is a derivation, and the other one is an endomorphism for now. It doesn't have to be surjective, just some endomorphism. Okay, so I write it here that delta from K to K is a derivation, so an additive map satisfying the Leibniz rule. And on the other hand, sigma goes from K to K, and this is an endomorphism, field endomorphism. Okay, so that's this. I'm going to fix this data, and now what I do is I'm going to think of a system of equations involving delta and sigma. So it should be, right? Okay, now consider a system, say of the form F1. F1 has some variable x, and then it has delta x, sigma x, and then you start composing sigma and delta. So maybe I don't know, delta square, sigma square, and then maybe delta. Oh, sorry, I forgot to say important. I'll write it here. This is important. Is that unless I say otherwise, I'm going to assume throughout the talk that they commute. Okay? I'm going to assume that these two operators commute. This is what I meant before, but they interact with each other. I meant that they commute. In other words, that sigma is a differential endomorphism. Okay? So this is the structures that we're going to be working with. Fields equate with derivation automorphism, but they commute with each other. Okay, so what that means is that when I iterate, I don't have to look at, if I look at delta sigma, I don't have to do sigma delta. Okay, and then you keep iterating. Maybe you get to some delta, I don't know, something like this or something. I don't know, to some iteration, right? And then you say this equals 0, and then you consider, finitely many of them. I don't know, dot. Okay, so this is just a system of differential difference equations. Does that make sense? Yeah. If something looks fishy, please Do let me know.
And these F's are polynomials?
Yes, good point. Yes, thank you. Exactly, where the FIs are polynomials in some variable, some number of variables over K, over this fixed ground differential field. Yes, thank you, good point. Okay, that's it. This is a system of differential difference equations. I'm going to call this DD system or DD equations. Okay. Now, what do I mean by I want to find a solution? What do I mean by that? Okay, so what do I mean by finding a solution? Okay, so now what I'm looking for, how do I say this? Okay, problem or question, if you like. Give necessary and sufficient conditions such that we can construct extension, right? I can construct an extension, write it like this, with L having a solution. Having a solution. Having, say, some point which solves the system. Yes. For today, I'm going to keep it in single variable, but everything I'm going to say works for a tuple. Okay, it's just that I'm going to draw some pictures, and the pictures look better in one single variable. But yes, definitely, this can be done for X, a finite tuple. Okay. Okay, so I wrote this A as a singleton, but in case the system is in several variables, then this is an n tuple, right? And what do I mean by solve the system? I just mean you plug it in. Wherever you see an X, you plug it in for X. And you get 0. Does that make sense? So the restriction here is that you need to somehow build this L, which has this derivation on it from L to L, a sigma on it, L to L, where they commute, and a solution, of course. Does that make sense? That is sort of the difficulty. Okay. Okay, so this is all the problem. Now, how am I going to approach this problem? It's going to be as follows. The approach I'm going to take is the following. So, in this system, you're sort of given some algebraic data up to certain order, up to order, say, like RS, right? Up to this kind of order, you have some algebraic information coming from the FIs, right? So what I'm going to assume, okay, is the following. Suppose we're given K, and then from K, I have some field extension, right? Field extension generated by some singleton A. So right now, there is no operators going on. But now, suppose that you somehow have that you can build operators going from KA to some field extension, possibly larger than KA. Okay, so from here to here, there is a delta, and there's also this sigma. Okay, but it doesn't go from KA to KA. It goes from KA to some extension. Okay, so something to keep in mind, or I like to keep in mind, is that you sort of have this system, right? And this system is giving you some algebraic relations between A and the delta sigma A. And that information is encoded here in this extension, right? But, okay, and then of course, you might need to go a little bit higher, you know, some extensions, and you get to the last one. So let me write it like this. Okay. So in this tower of fields, I am encoding whatever algebraic relations were given by dfs. But it could be that none of this is an honest differential difference field because the operators might be going outside of it, might be going to the extension, right? Okay, so now suppose you're given this data, these field extensions and these operators going to the extensions, right? And now if you want to find a solution, what am I trying to find? I'm trying to find an honest differential difference field, so one where the operators go within itself. Well, it will be very nice if you can continue this tower. I can build the next iteration of this tower, and then I can do it again, and I can do it again, and I can do it again. And if somehow I'm able to do that, then I just take the union. And then what I get is an honest differential difference field. So this is a question here, whether you can keep going. Okay, so I'm going to use this notation, then I'm going to call this guy L00. I'm going to use this, I'm going to call it LRS, just to denote what sort of compositions I got. And then what we want to do after this process is build L infinity infinity. Okay, so this is sort of the goal. Given the data up to here, can I keep going? And of course, in general, you can't. If you just give me some random data here, right? It's like, I'm just going to use some random data here up to here, right? Then in general, if you want the delta and sigma to commute, it's impossible, okay? So what you need is to give me what are the conditions, some sufficient conditions up to here, which tells me, look, under those conditions, then I can keep going. Does that make sense? So that's sort of that is the problem.
Have you assumed both the characteristics?
I have not assumed, yeah, that's right. Good point. So right now, K is arbitrary characteristic. So I should say that K that we fixed there is arbitrary characteristic. So what I want to explain today is, okay, first of all, give the conditions here, but there are certain conditions in which in characteristic 0, you're done. And they're actually quite reasonable conditions. Oh yeah, under these conditions, characteristic 0, you're done. But then it turns out that those conditions do not work in characteristic P. There are examples, so you need to give more conditions. And you're like, I can give more conditions and I make it work, but you have to show that those conditions are also necessary. So you don't want to give, too many. So that's the point of today's talk. Explain the difference. So, okay, let me say in that language, in characteristic 0, we know there is a model companion. And what I'm about to do is going to give like very explicit axioms. Okay? In DCF0A. And then the complications in characteristic P, I'm going to show you a way around them to get the model companion as well in characteristic P. So DCF-PA. That make sense? Okay. No. Yes. That's right. So here I have an honest, this is what I call an honest differential difference field because delta and sigma go from K to K. But once I move to the extension, this A, it doesn't go back. It might go to some extension and then it goes to some extension.
Construct a sigma.
Yeah. Yeah, I'm saying that, yeah, you're given this data. Yeah, you're given this delta, you're given the sigma, and then you're given a delta, sigma again, up to this length. That's what you're given. So under some assumptions, then you're good to go, right? Exactly, yeah. So I'm going to talk exactly about that. I'm going to talk about what the issues in characteristic P is separability versus inseparability. And that's what I'm going to talk about exactly. Okay? Okay, any other questions? Okay. So, sorry, I'm not sure I want to, okay. So this is blocking kind of the way to this, oh no? Is that okay? Yeah, in the back, is this okay if I write on this board? Okay, in that case, I'll just move on to the next one. Okay. Yeah, actually, it's a good idea to write here. Okay, so let's think about this problem. I'm gonna draw a picture. Okay. Picture. Okay, this is picture. A, A. And then I want to think of going up as applying delta, right? So if I'm here, then so the next element in this grid, I'm thinking of this as a grid, you know, what is it, n squared, you know, positive quadrant, something. This is like delta A, right? And then, you know, delta 2A, going up, delta. And then going to the right is sigma. So here's like sigma A, here's like sigma square A, and then of course here is delta sigma A. I mean, you can imagine what happened. So I'm looking at this grid, right? And so what I'm given, if you look at this data, what I'm sort of given is some rectangle in some sense, okay? I mean, it doesn't have to be a rectangle. Let's just assume it's a rectangle, okay? So you're given some information here, right? Let's just say for now that what you're giving me is just this rectangle here. So I'm gonna go say up to here, let's just to draw something for you. So let's assume that the data that you're giving me, this tower of fields is just this rectangle. Does that make sense? We have A, I can apply delta to delta R times or something, and I have sigma A, and I can also apply delta to that certain number of times. Let's call this R or something. Makes sense? That's the data that I'm giving. Okay, now you can break this problem into two. The first one is that, okay, let's have a look what happens here. What happens here? Let's say that the first thing you want to do is I want to go up all the way. I just want to go up, you know, looking in this first vertical line. I want to go up. Okay, and then as Jason was suggesting, is that you just have to understand what's happening here. So let me write it here. Case one. Okay, so maybe I should say, to go up, we know how to do it. Okay, so we consider three cases. Let me write it to maybe here. What you have to understand is in this guy, this is delta RA. Delta RA, what are the possible algebraic relations of delta RA over its predecessors? That's it. So delta IA has some algebraic relations over its predecessors. Okay, and so you just write three cases. Actually, I shouldn't have written this. Just put here. Now you have case one. Okay, if this algebraic relation over the predecessors is separably algebraic, then you're in a very good position because there is nothing to do. If delta RA is separably algebraic, then it turns out that to build the next one. Sorry, I think this is blocking me. I should have done that. Let me just write it a bit better so you can see. Let's say here is the delta R. Here is delta R, and I want to build the next one. I want to build delta R plus 1A. This is the question right now. Okay, if this is separably algebraic, say with minimal polynomial F, then you have no choice. You have no choice. Oh, yeah, sorry, over the predecessors, over K. So I'm looking at this guy, and I'm saying this is separably algebraic over everyone below it. So this K, A, 2, delta R minus 1A.
Just the derivation.
Yes, I'm just looking at this vertical line at the moment. Okay. Okay, and then there's nothing to do. This delta R plus 1 is given by, there's a standard formula. It's given by this. F prime. Anyways, there's no choice. Like this is what the delta R plus 1 has to be. Right? No choice. Okay. Now, 2, if in the case that this is transcendental, say transcendental, over again the same predecessors, then in this case, again, standard result tells you you can choose the delta R plus 1A freely, completely freely. Just choose it freely, whatever you like. Just choose whatever. You know, if you like certain thing, choose that. Completely free. Okay. Now I am missing one case in which is separably algebraic. Sorry, inseparably algebraic. So if inseparably algebraic, and it turns out that in this case, it's not always possible to extend it. Okay, this is okay. It's just in general, it's not possible to do the extension. but we know exactly when you can do it. Okay, then it's only possible when the minimal polynomial, say f, is over the constants of the differential field. Yeah, some constants going on here. I'm going to write it just over constants. Over constants. And in this case, once it's over constants, you can choose, like in the transcendental case, you can choose this freely. Okay? So in the inseparable case, there is only one subtlety, that if it's not defined over the constants, then you can't extend it. But if it is defined over the constants, you can extend it, and moreover, you can choose freely, whatever you like. Okay? So this sort of answers the question going up. Is that making sense? Sorry, I can give a few extra details, but if that more or less makes sense, then yeah. Okay. 3 cases, yeah? 3 cases.
Going up, you're not concerned with
so right now, yes, that's a very good question. Right now, I'm not, because all I'm doing is going up in this line, right? So the issue, if I go up in the next line, then I have to worry about that. So right now, I'm not worried about that. I'm just saying, look, the point case about extending derivations, this completely answers the question. Okay, now let's do the opposite and see what happens if all I care about at the moment is extending sigma. So I do it vertically, now I want to do it horizontally. Okay? Okay, so now say I want to extend things horizontally. So to go to the right, oh, by the way, sorry, I should have said something here. I do want to mention quickly is that in the differential case, separable case, I have nothing to choose, and moreover, this already lives in the previous field. If you look at the formula, it already lives in the delta R, right? And in the other 2 cases, if I can extend it, I have a complete, free choice. So you choose something very transcendental. Okay, that's one way to choose it, very transcendental. So that if you started with something separable, you can always perform this construction to give something separable. So you can preserve separability if you choose this to be just very generic, very transcendental. Yeah. So I want to make that remark. That in this construction of delta, you can preserve separability of the extension. This is important, okay? I'll go back to this later. Okay. Now, what happens if we go to the right? Okay, now let's go to the right. It turns out that going to the right is, a standard kind of field theory. It's just a sigma, right? It's just an endomorphism on a field where you might be shifting things a bit, but it's a standard, right? So if I want to go to the right, okay, I look at this guy. Okay. Sorry, sigma. Say sigma, say S plus 1A. Okay. Actually, I only have sigma 1, so I want to take, anyway, I write it at S for now. I only have S equals 1 at the moment, but okay. I want to say what this is. Well, we know exactly what to do, right? If this is, say, algebraic over the previous ones, sorry, no, I want to define this. So if this is algebraic over the previous ones, right? Well, how do you choose the other one, right? The sigma S plus 1, then sigma S plus 1A is any solution of F sigma T or whatever, where F is the minimal polynomial, right? This is just a standard field theory, right? Does that make sense? Standard stuff. And if it's transcendental, then you just choose the other one to be transcendental. Then just choose this transcendental. And so it's just standard field theory, right? I'm not going on. But what I do want to stress out is that in this case, in general, even if you started with a separable extension, right? Suppose that extension up to A sigma to the S is separable. in this, here there's a choice of solutions. There's a choice of solutions. So if something is inseparable, you might choose something inseparable. Even if you're careful, in general, you cannot produce a separable extension. In general, you cannot produce a separable extension. So if you give me certain data of sigma to sigma r, and I want to produce an honest difference field, just difference field, then this, you might not be able to get a separable difference field extension. Okay, and we were stuck with this for quite a while when I was talking to Kai, and luckily at some point I met, one of conference I saw Zoe, and Zoe told me like, you should read this paper, and then I read the paper, and then I saw her again, and I saw her, I read the paper, but I don't think, and she's like, no, go back and read it properly, read these statements. I mean, yes, she was absolutely right. This completely gave us the right direction of how to continue with this problem. So I do want to take the chance to say that Zoe was, to me, was a massive influence for me. Her work completely inspired all of the things that I've done. And I consider myself very fortunate that not only I had some sort of academic relationship with Zoe, but also a very amicable relationship with her. Okay, just wanted to take a chance to say that. Okay. The following is due to Zoe Chatzitakis. Okay, under, I don't want to give many details, under a certain configuration, which I'm going to call Chatzitakis configuration, you can produce a separable difference extension. So even though in general you can't, there's a certain configuration that's happening up to order S, that if you give it that configuration, then you can always find a difference field extension in which the extension is actually separate. Okay. Any questions right now? So all I've said is that you can go up, right? You can go right. And going up, you can preserve separability. Going right, you have to be careful. Okay, but if you have this Chatzitakis configuration, then it's fine. Okay, but now, now let's draw the picture again. Okay, again, this is A here, delta here, sigma here. And I suppose that now, again, I'm just given up to sigma A, and I'm given up to some up to here. Here is R. I'm going to try to draw some of the dots. Dot, dot, dot. Okay. So this is what I'm given up to R and just to sigma 1. Okay. And yeah. So this is the this is my okay. This is what I'm given. This rectangle. Okay. Now, I want to say now. Assume the following. Okay, so I have this. Okay. Let M be a natural number. Okay, and assume the following. Number 1, assume that R is larger or equal to. I want to get this right. Sorry, it should be that's 2 times M plus 1. Yes. That's it, sorry, yeah. So suppose that I have this R, suppose the M is here. So now think of me having like this rectangle where I have a sub-rectangle, which is smaller. How small is it? Well, it's this, so it's very explicit numbers, right? It's just kind of almost just like double of it. It's almost just double of it, okay? Now, what is the assumption is that I have this and that. In the gap, what do I mean by in the gap actually? In the gap, I mean here. I mean like here. In this gap here, I have no mu algebraic relations. Okay? Suppose that all the algebraic relations that are happening in this rectangle, all of them happen in this bottom rectangle, all of them. So here, there are no new ones. Okay? So there are no new algebraic relations in this top rectangle. Okay? So remember that when I say algebraic relations, I always mean over the kind of the predecessors in the grid. So you could have some algebraic relations here, but they all come from the ones already happening here. Okay, so there are no new ones in the sense of this over the predecessors. Okay. Okay, and then what happens is the following. Okay, say I want to now extend the whole rectangle going up. So now it's not just the first vertical line, but I want to extend these two vertical lines. I want to extend the two vertical lines all the way up. Okay, well, you remember the differential context test tells me that as long as in this bit, okay, I'm waving my hands a little bit here, as long as this top bit is not inseparable, right? This was the point. Did I erase it? Oh, it's behind this. As long as this is not inseparable, then yes, I can just extend it and extend it freely. Well, this condition in the gap is much stronger than that. This condition in the gap tells me, like, look, any inseparability issues only happen in this bit. Okay? But as long as I have it here, then I can go up. So I can definitely go up. I can extend the delta, just go up. So now I can go all the way up with the delta. But now you can ask me, like, okay, you went up with the delta, but how do you know that you can actually do the sigma as well? How do you know that this choice that you did on the deltas actually tells you that I can map this to this under an endomorphism, right? And by the way, I made this choice, I made the generic one. You know, I told you that you can choose things freely. Well, I choose like transcendentals every time. Turns out, and I'm not going to give details that, it turns out that, how do I write it? Okay, I'm just going to say it. That this gap does the job. So this is where this gap comes into play. The fact that this gap is kind of big tells me that indeed, if I choose this guy, then this guy, there is an endomorphism going from this guy to this guy. Okay, I'm not going to give details because it gets a bit technical. But this is the magic number in order to do it. This 2n plus 1, okay? And if you have an n tuple, you have to put an n in there, but it's polynomial. So this gap is polynomial in everything, in all the data. Okay? Is that more or less okay? I'm omitting many things, but I think it makes sense to omit them. So exactly. So it tells me that if I'm only looking at this rectangle, I can go like this, and that's the same as going like this. Exactly. That's the whole point. That's the whole point. Okay? That's the whole point. And then you can just keep going. Okay, now a remark here is that in characteristic 0, I'm done. You're like, wait, what do you mean? Why are you done, right? You still need to tell me what happens if I go to the right. I've only done this rectangle. Well, this is just like general stuff that in characteristic 0, if you give me a differential endomorphism like this, it can always be extended to some big differential field. This is, I mean, from in algebraic terms, this is because in characteristic 0, sort of the differential isomorphism type is determined by differential equations. And then you take a universal field and then it works. Model theoretic terms is because you have quantifier elimination, therefore any homomorphism is elementary, kaboom, saturated thing, and that's it. Yeah, sorry, I tried to explain it from both sides. I hope it kind of makes sense. But anyways, in characteristic 0, once you have this information, you can just do it. Abstract stuff, okay? Okay, so if I wanted to say, okay, you know what? I want to solve this problem in characteristic 0. Once you have this bound, then you're done. And sorry? So whenever you give me, so going kind of the other way, whenever you give me a problem like this, right? If you assume that the extension you have is separable, then yes. Yes, that's right. So this is what I was kind of making a big fuss about separability things. So I'm only concerned really, I didn't say it here because I didn't want to add extra information, but I really want to find extensions that are separable. And if you impose that, then yes, you can always take a separable thing, and then there is a result that we proved in the paper that at some point, you get this thing. You always get that all the algebraic information is to a certain finite number, and then you can just find the gap. Yes.
I've lost track of the goal. So there's this discussion about the field and the operators on the field. But what about the solution to the original system?
So if you're able to if you're able to complete this grid all the way there and there and there and there, that gives you this field extension. And this field extension is an honest differential difference field, meaning the delta goes from this to itself, the sigma goes from this to itself,
Right.
and so I'm able to build this L.
But the A, why does it solve the original?
No, this A will solve, this A I started with will solve,
From the beginning,
yes,
solve.
yeah, this A will actually solve the system. Yeah, the point is that you're starting with this candidate. This is just like a candidate, like, oh, I think this should solve it, right? Because this tower has the information of the system. So it looks like this A should solve it. The problem is that none of this is an honest differential difference field. So you want to do that. This is why this infinity comes in. Because I always, whenever I talk about solutions, I do want my operators to go within the same field, right? So it's a good candidate, but you need to make sure that it's living where you want it to live. That make sense? Okay. Now what happens in characteristic P? In characteristic P, this thing about extending automorphisms, whatever argument you want, it doesn't work. There are examples in which you have a differential embedding and it cannot be extended. Right? In characteristic P, you can't do it in general. Okay, because these maps are not what is called elementary. Okay, in general. So you have to kind of you have to do something else, right? Okay. So that makes sense? Sorry? These maps are not necessarily elementary, so you can't use this abstract argument.
It's a failure of quantum elimination.
That's right.
For what?
DCFP. Yeah. That's right.
I define a solution system guarantees
So, so can you see the last bit again?
the aim I thought was to find conditions on the system without
Yes.
to have actual solution.
Yes.
You
Yes. So notice that basically this system, I'm sort of encoding it in this tower of fields. So instead of thinking of the system, I usually just think of this tower of fields. Does that make sense? Because if you have something, if it's telling you like, oh, this is telling me this is algebraic over the other one. Yeah. So this is already appearing in this field extension, right? And so when I say what conditions I need in here, I can now just refer what conditions do I need in this tower. And precisely this is more or less what I'm saying here. Like if you have this condition on the tower, then you can do it in the going up. And in characteristic 0, that's enough. So something that I was hiding on the rock is that the S, I can always make it 1. Yeah, linearization process, you can always add more variables, and yeah, I was kind of hiding down in the rock, but you can always make the S 1. So was that more or less a question that?
No, but I mean, the L they're different R, different S.
Possibly, but you can just make them all the same. Yeah. You can just take the same RNS. If one is less than the other, just increase it. Yeah. Okay, so is that okay? Any other questions? Okay. Okay, so in characteristic P, you have to do something. Okay? This is not enough. This assumption is not enough. I have to put another one. So assume what I called in the Chatzidake's configuration. So assume that in this bit of the sigma, so assume, what is it? No, sorry, actually it's just this bit. Assume that in this subrectangle, I have what I haven't told you what it is. I don't want to say it. I have a Chatzidake's configuration, and what that gives us is that I can extend the sigma to the right and obtain a separable extension. So that's that. Sorry.
You tell what kind of thing it is?
Yeah. So it tells you that, okay, assume that this bit is algebraic over the previous bit. Okay, that's one thing, and that you have a certain separating transcendence basis of a certain length, right? Where there is a subtuple in which you become separately algebraic over certain p powers of the given separating basis. It's something like that. So, but yeah, it will take me maybe a few minutes to properly write it down.
Sort of field.
It's a completely field, it's a field arithmetic on A and sigma. So the way that it's written is in the paper of Zoe is suppose you have, U algebraic variety, V an algebraic variety of the sigma prolongation, right? And assume that the function field of V has a separate transcendence basis with a certain configuration. That's it. And then you get this separable difference extension. Does that more or less make sense? Yeah. Yeah. I mean, I think I have the paper there, or at least a statement of the theorem. Okay, so you can do that, and then you can just go all the way. Okay, so now we have this bit, and we have this bit. Is that okay? But you're like, oh, but you're missing a big chunk in here, right? Like, what about this chunk in here? It's like, oh yes, you're right. What do I do now? It's like, oh no. Okay, so let me skip one detail, but now say you're giving me this, and now I want to say, look, I'm going to call it star. I want to build this guy, right? I want to be like how sigma does here, what delta does here. That's more or less, right? I don't have this point. I don't have it. I just don't have it. But I want to say, look, I can build it in a way that things commute. Okay? And you have to consider what happens. Let me do it. I'll do it here. You have to consider two cases. I'm just going to do one case. Case one. Okay, case one is that suppose I take this guy. Okay, how do I call that guy? That guy is n plus 1, comma, and this is just 1. So I just don't want to make the notation. I don't want to introduce the notation, but it's sort of convenient to write it like this. Here I mean apply delta this many times and apply sigma this many times. Okay? I didn't want to introduce the notation, but it's convenient. Okay? So case one, assume that this guy is transcendental over his predecessors. Over his predecessors, right? Okay. If this guy,
the predecessor is not just down, but down into
in this case, the predecessors are actually down. In this case, the predecessors are with respect to this rectangle. Let me remember. And with respect to, yes, with respect to also all of these ones. Yeah, all of these ones. Suppose it's transcendental. I kind of feel like in this case, if I remember correctly, I think you only have to consider this, the whole rectangle, definitely. But I think you have to consider this rectangle and this bit. Yeah, I feel like this bit doesn't matter because of the choice that you make. Yeah, that's right. You make certain choices in here, and you only have to consider predecessors in this rectangle and this tiny bit here. Okay. Suppose it's transcendental. Then how do I choose this guy? Well, I choose it to be transcendental again. Okay. Then choose the A m plus 1, 2 to be transcendental. Okay, a new super transcendental element. Okay, but then you're like, okay, it's like a random choice. You have to check that it works. You have to check. Look, this square commutes. That's what we have to check. I have this tiny square. I want to check this square commutes. Okay. So let's see. First of all, this does give me an automorphism because this guy was transcendental over this. So this will be transcendental over this. Okay. Fine. This is an automorphism here. There's a delta here. Okay, this bit is fine. Now I need to go the other way. Okay. If this guy was transcendental, then this guy has to be transcendental. Okay. This is standard stuff. Okay. If this guy was okay. Anyways. If it wasn't, then this wouldn't be. Okay, anyways, this has to be transcendental. Okay. Oh, no, sorry. This could be, if this guy is transcendental, then this could be, yes, sorry, inseparable. Yes, that's right. That's right. That's the problem. Yes, I was about to miss the subtlety. Yes. So this is transcendental. This could be transcendental, in which case it's actually okay, but this could be inseparable. Okay. So the problem would be like, say that, which guy is it? Is this guy, right? So this guy is AM1 is inseparable. Okay, suppose that this guy is inseparable. Okay, then you look at this guy. Now I'm going to ask you, what could this guy be given that this is inseparable. Then this will be what? Over the predecessors. It's still inseparable, but could it be separable now? Let me write it. Let me write it. For sure, this guy, when you apply it again, let me write it. For sure, sigma of this guy is inseparable over the shift. I'm just gonna write it like this. Sorry, because I don't want to get into just sigma A actually, because so one sigma. So over the shift, right? So whenever you have something separable here, and you move it, it's inseparable. Oh, sorry, sigma square actually. It's sigma square. So I'm moving to the right to sigma square. So yes, over sigma square of the other one. So it will be sigma, sigma A. Yes, that's right. Okay. But so this is inseparable. But it could happen. This sort of things happen in field theory. But it could be separable over K A sigma A, because you have this extra thing here. So once you add extra parameters to your bottom field, you might mess up inseparability. It might just become separable right away. And then once it becomes separable, you're in trouble, because once this is separable, then the choice going up is not free. The choice is completely determined. And this was for us, again, another obstacle that we were just like, oh, we don't know what to do. What if this happens? Well, it turns out that you can show, and this was a proposition we proved, because this extension is separable, this issue of going from inseparable to separable, it stops at a finite number. It just stops happening. This could happen, maybe 7 times or 20 times, where you go from inseparable to separable, but it just stops happening once the extension is separable. Okay, and then you do a reshuffling of things, you relabel stuff, then you can assume that this cannot happen where you are. Okay, I'm sort of waving my hands a bit, but you have to prove something so that you can avoid this. So this can just cross it out. And so if something is inseparable here, then this is inseparable over the predecessors. And then once it's inseparable, remember that you have to show that the coefficients of the linear polynomial are over constants, then this is fine. This is the main point I wanted to make. That in characteristic P, you have to deal with 2 things. First of all, build a separable extension here, and then show that once you have that, this is the main obstacle, but this doesn't happen up until finitely many times. Okay? And in fact, that number is just M. That is just we computed the number is just M. After M, it stops happening. Okay. So does that more or less make sense? Oh, sorry, I hope it makes sense. I know it's a bit technical, but hope I'm explaining at least what the problem is and how we resolve it.
How do you deal with those first n steps?
First, right. So the assumption here is that you start with something in which, you already have a box of size m times n. Okay, yeah. So I wanted to avoid doing that, but the assumption is you already start with that. Okay. I just wanted to do the case of one iteration of sigma, but yeah. But as I said, usually when you have something of sigma composed m times, you can rename variables and sort of bring it down to order 1 again. So yeah, it's a reduction process going on here. But okay. Then once you do this, then you just kind of repeat the process now. And now I built this star, so good. And then I built another star, the same process. Once I do that, I just keep going. Okay. So the point that I'm trying to make now is that now these conditions are the 2 I wanted. These are the sufficient conditions. Okay. So if you give me some data like this, and I have this gap, and I have a configuration like this, then I can complete this tower of fields to get a solution. Does that make sense? And now I just want to finish saying, like, well, how about this being necessary? These are sufficient. How about this being necessary? Well, okay. If you give me, so maybe I write it as a theorem now. Theorem. says that suppose you give me A, suppose you give me two assumptions, then there exists this L infinity, comma infinity. Okay, you can do this. Yeah, that was the goal. Okay, now how about the opposite? Well, suppose that you do have a solution to your equation in some differential difference space like that, and assume that this extension is separable. Okay, so for the converse, you need to assume this is separable. Then you can reshuffle things a little bit, okay, not too much, so you don't actually affect the system. You can do it in a way that you don't affect the given system, but you reshuffle it a bit so that you get this and you get this. Yeah, so there's a converse as long as you assume this is separable.
Like not separable algebraic, but some separable.
Separable in the abstract field theoretic sense. Yes, yes. So, right. So, for instance, so let me write it here. If over K is separable, we get a converse. And let me explain what I mean by shuffling things. We get a converse. Okay. So suppose that you give me the system and you give me the extension where I can find a solution, and that extension is separable, right? Okay. Now I look at the order of the system. Say the system has order 123, right? Okay. Then the separability assumption tells me that if I go probably larger than that, at some point, my algebraic relations will stop, the new ones. This is something we had to prove. Okay, if you're going up, the algebraic relations stop, maybe they stop at 225, right? Well, then I take my R just to double the 225. But the reason I can keep going up is because you gave me from the start already something to work with, right? So you gave me this field. So whatever order you give me, I can construct it because I'm given it. So I just kind of, if I start with this, I want to find the M, I want to find the R. And this data just comes from the equations. Okay, so I can find the R. The R will be some, the M will be a number large enough such that it includes all of these orders. All the algebraic relations happen this bit, and then I just take the R doubling that. Okay. How do I get this? This is the tricky bit. This is definitely the trickiest bit. In that same paper of Zoe, there's a theorem telling you that if the extension is separable, you can again reconfigure things to exactly get this configuration of Zoe. So Zoe needed both directions as well. So I should say here that this paper of Zoe is where she proved that separably closed fields of arbitrary degree of imperfection, you can add a generic automorphism. So she had to deal with the same problems that we did. But luckily she did it, and we didn't have to do it again. So we were using all of these things that she was able to give the necessary conditions and sufficient conditions, and we just used them. And so yeah, whenever you have an instance like this, you can shuffle things a little bit. You have a transcendence basis, but you want to be separated to transcendence basis. You have to and some of them might be transcendental, so you have to move things around a bit. But you just write it in this separated transcendence basis so that the rest of the elements are separable over something else, and you get it in that form. But I think it's tricky, but it's possible. So anyways, so does that more or less answer the question?
Same with first there exists an M so that all of the just not that finite stage, and possibly increasing the M slightly.
Yes, exactly. And then possibly here you don't have Chassik's configuration. Well, you go a little bit to the right to get Chassik's configuration, but then you can always do that. Yeah, so there's a bit of like going up and then going right, and then relabeling the variables so that you actually get in a good situation. And I can give a bit more details, but I think I run out of time. But this is the conclusion, and what this tells us is that you can always sort of, in an effective way, decide whether such a system has a solution or not. And this gives us what Anand was saying about this model companion. So let me just kind of say here, what Anand was saying is that this tells us that this theory, if this doesn't make sense to you, don't worry. If it makes sense, then it makes sense. Okay, so this is what we were interested in this. UCFPA exists. So what do I mean by that? I mean like the theory of differential, I'm gonna write delta sigma. Delta sigma fields has in characteristic P has a model companion. So what Zoe proved was that separately closed fields in characteristic P of different separately closed fields of characteristic P, the different perfection E, you can add an automorphism. This is so. Ross is slightly different. That makes sense? This is always result. And I have to say here that, as I said before, this we knew. This we knew. This is from UDIS 2000 and something. But I don't know, when we started working on this, we were like, I mean, this seems quite natural. We know this one exists from 25 years ago. We should know something about this one as well.
And the underlying fields are pretty clear.
No. In this case, no. In this case, no. It's separately closed. This the underlying field here is a separately closed field of characteristic P, and it's always infinite Ershov invariant. It's always infinite Ershov invariant.
So the underlying differential field is like Carol's field.
Is like I mean, sorry, the underlying field in terms of the
The underlying field, sorry, the underlying differential field
is differentially closed in the sense of Carol Wood.
is Carol's field.
And now, by the way, things are very weird if you don't ask things to commute. If you don't ask sigma and delta to commute, then in characteristic 0, there is a model companion. If they don't commute, in characteristic P, there is not a model companion. So it's a kind of dichotomy when they don't commute. But if they commute, it turns out that, hey. So say it again, when they don't commute?
Is it possible for them to have a higher order relation?
Well, when they don't commute the set of terms that you build here, you have to consider both iterations, right? Like sigma, also sigma delta will appear in here, right? But the reason of the non-model companionability has to do more with the fact that, for instance, one way to show it is that you can take an existentially closed model where the sigma is not surjective. And that's just kind of weird. Anyway, so yeah.
Maybe we should ask you,
I'm sorry.
instead of commuting, you ask for some other identity.
Oh, sorry.
Then
A
you will-
higher order relation.
Yeah.
Oh, sorry, higher order relation. Yeah, no, I said sorry. I know. Yeah, sorry, I completely missed the point. I don't know. Quick answer. I don't know.
Yeah, one thing we could look at is like the León version.
Yeah, you could take like, you mean taking like sigma derivations and the,
Or even if you look at sigma inverse, sigma, that's a new derivation.
yes,
And you could look at all these derivations and look at the León.
right. And ask that as finite dimensional, right? Yeah.
That be of this finite dimensional, can you just find a commuting basis?
It is likely that you could find a compute. Yeah, I guess, I mean, as long as you can do it, as long as you can find one in which they are linearly independent, then you can find commuting ones. And usually finding one where they are linearly independent is very tricky. Yeah, so you have these sigma inverse delta sigmas where you vary sigmas, and yeah, I guess maybe you want some fair dimensional thing, but you need to know that these guys are linearly independent somehow. So maybe, but I think there's something to be done about linear independence, because in general it's not true, right? You cannot find a basis of commuting derivations if you don't know that things are linearly independent already. So yeah. Anyways.
kind of blended into the question.
Yes, I know. I know.
You're done?
Yes, I'm done. Yes.
None of those questions were like on the record, I guess. But